presentation. Yeah, so because I cannot assume that everybody is familiar with class algebras, so I will basically give some gentle introductions in the overview sections and introduce the main results. So here in the first part, there will be no rigorous or detailed mathematical techniques. And then in later part, I will be more precise about the mathematics part. Okay, so what is a class algebra? So let us first recall some familiar concept from what we have learned in the university. So what is a manifold? An m-dimensional real manifold, it is just a gluing of many pieces of neighborhood. And I use T to index neighborhood Vt, such that each neighborhood Vt is homeomorphic to the m-dimensional real vector space, right? So this is what how we understand a manifold. But in mathematics and also in physics, it is often useful to, instead of consider this geometric object, it is useful to consider the functions on this geometric object. So here, then let us consider smooth functions on this manifold. Then in this way, for each choice of your neighborhood, you can express any smooth function in terms of the local coordinates, right? So local coordinates, they give you isomorphism between neighborhood and real vector spaces, and now you can write rational functions in terms of them. And in terms of quantization, so if you work with physics, then when you want to quantize the classical mechanics into quantum mechanics, you simply replace this commutative algebra of these smooth functions into some non-commutative algebra. So in this way, that by considering functions, this allows you to talk about the quantization. And now class algebra can be imagined in a similar picture. Rank M class algebra, I intentionally use the same letters. This is simply an algebra endowed with clusters of distinguished elements called class variables. So here in your mind, you can imagine the clusters is like a chart, and a cluster it consists of M elements. This is like the M local coordinates on the manifold. Right? So this is analog. And now we require that every element of the algebra is a rational functions in terms of these local coordinates. Now, because we are working with algebra or say algebraic geometry, so instead of consider smooth functions, we consider rational functions and polynomials. And for historical reason, actually, when we define class algebra, we usually require more structures than what we have seen above. So first of all, we require that all clusters, or say all neighborhood, they can be constructed from an initial one. So namely, if you are start with only one cluster, then there's an algorithm tell you that how you put more clusters, and then how you can glue them into a big algebra. And moreover, we require some very special transition maps between adjacent clusters. Right? These are for historical reason. And the second condition is, in some sense, is too restrictive. And nowadays there are some progress by kind of generalize the transition maps, and this will lead to the concept of generalized class algebras. All right. So in this point of view, a class algebra is simply an algebra with a lot of charts on it, or roughly speaking, you can imagine that it is a manifold in some sense. And now usually we'll be talking about class algebra, or more precisely the so-called upper class algebra in this talk. I denote it by A. So over the real numbers, it usually takes this form. So it is the regular function rings on some algebraic variety, or say on some schemes. And here by regular function, I mean the collection of rational functions which are regular everywhere, right? So this geometric object, this curly A, this is again a union of many pieces T. And each neighborhood, this piece is T. In this definition, in our class algebra theory, it is simply a torus. So this is a dimension M split torus. Or it might be a partial compactification, namely you replace R star, the non-zero real numbers, into by adding the zero. So this you can kind of partially compactify this torus. So we might consider both situations, and once you glue this by transition maps, you obtain the corresponding geometric object A. And moreover, because every function is a rational function in your chart, so actually this chart is dense in this geometric object. So in algebraic geometry, we say that it is dense in the Zariski topology. So in some sense, class algebra, this is a very special regular function ring. It is over some geometric object which has a very big torus inside it. So it is basically a torical variety. And then we have a notion that we'll repeat again. So we have something called class monomial, namely you choose any cluster or say any chart, and you form the monomials from the local coordinates in this chart, and this will be called a class monomial. These are some special elements. Okay. If you have any questions, just interrupt me. So these are the class algebras, and now let us consider some natural problems. So one important problem in the theory of class algebra is to express distinguished functions in terms of the local coordinates, right? So some functions, they have very beautiful expressions. For example, this will give you some fascinating combinatorics. And in this way, by taking the local form of these functions, you might also recover some well-known functions, such as characters of modules and, sorry, this is not invariants, some Alexander polynomial, whatever. And also, because the algebra is a vector space with a multiplication, so it is natural to ask for basis of this vector space. This is a very natural and fundamental problem. And once you have a basis, you have a precise control of the size of this vector space. Usually, this is infinite dimensional. And then this will allow you to solve many problems. And moreover, this is today's topic. We are looking for some very special bases called analogs of the Duke-Null basis, which arise from the Lie theory. All right. And there is also a very important subject, namely we want to discover the higher structures which are hidden behind these algebras. So this is the so-called categorification. Namely, for example, when instead of studying the natural numbers, you are going to study, you view them as a dimension of vector spaces. Therefore, by viewing the numbers, replace the numbers by dimensions of vector spaces, this allows you to work with more structures, like you have linear maps between vector spaces, which cannot be visible at the level of numbers. By taking categorification, then you study the algebras at a higher level in the categories, then you can have more operators to work on. And it is also important to consider the connections of class algebra to other fields. For example, nowadays we know class algebras, they are ubiquitous. Because in some sense, you see, this is just an analog of the definition of the regular functions rings of some geometric object. So this is a very basic concept. So they can appear in many areas like combinatorics, representation theory, Lie theory, Poisson geometry, algebraic geometry, topology, dynamical system, and so on. So I will not cover these topics today, but there are many people working in different directions. All right. So let me talk about the motivations of today's topic. So we go back to the origin of the theory of class algebras. We like the base ring K to denote the integers, real numbers, or complex field, whatever, or the quantization, where we use V to denote the quantum parameter. And then Fermi and Zaminsky, about 20 years ago, they invented class algebras to study something called total positivity of matrices and the so-called dual canonical basis of the quantum group. So this is a quantized golden ring of a unipolar radical n. So you can imagine that this is a manifold consisting of the upper triangular matrices. And then they expect that for many varieties, such as n, which arise from Lie theory, its coordinate ring or quantized coordinate ring are class algebras. And moreover, this class algebra has a basis, which is an analog of the Duke-Null basis for Kn, and such that it contains all class monomials. Recall that these are the monomials of the local coordinates from the same cluster, or say from the same chart. Yeah. And if we do not talk about the general varieties, but instead we focus on the original quantum group Kn, then we have the following natural conjunction. So for the quantum group Kn, its quantum class monomial should belong to this the original dual canonical basis. Right? So instead of talking about the analog, we are talking about the original one. And this was one of the motivation of class algebra, and it has been open for many years. Recent years, a proof in full generality was given by my talks or by a series of my papers by introducing something called common triangular basis. I will explain that later. And there's a different approach by work of Kashiwala, Kashiwala, Kim O, and the later work by McNamara, which will give you a different way to prove this conjecture based on categorifications. And now, this original version, Kn, has been well understood. But the natural question is, how can we understand the analogs of the Duke-Null basis? And how can we go beyond this N? We want to really study the more general varieties A. Okay. So the analogs of these dual canonical bases was proposed in my approach, namely I proposed common triangular bases. And by definition, these bases contain all the class monomials, and it is something called a Castanuski type basis, which I will explain later. But to be short, this is something which is computed using a recursive algorithm analogous to that for the famous Castanuski polynomials. Right? So we have an analog now, and this analog is good because for quantum groups, for quantum class algebra, which are just the quantum groups, the common triangular bases defined in this way are exactly the dual canonical bases. Therefore, in vast generality, this basis is kind of generalization of this dual canonical basis. And moreover, the Fermi-Zariski conjecture is true because this B star is our defined basis L, and by definition, this basis L contains all class monomials. Therefore, we obtain the conjecture for free. Okay. So in this sense, we have answered the first question. We have a good analog. And the next question is, can we really go beyond this quantum group and study more general varieties? So this will be today's main result. I need to go first with some concept I call a based class algebra. This is a pair of class algebra A with a basis. So this is a naive definition. And I require that this class algebra endowed with this basis has some natural properties. I will omit the definition, but just say that these are natural and they're analogous to Lustig's definition of modules with basis. Okay. And then we talk about its categorification. Assume that there is a monoidal category, and we want that the growth-centric ring of this monoidal category, which where the product is given by this tensor product, it is isomorphic to our algebra. And moreover, the basis elements are exactly the simple modules in this monoidal category. So this is a very strong expectation. And in practice, it's usually unknown how to find such a category because, as I said, class algebra is a very basic concept and it can exist in many situations. But the monoidal category has been constructed for very few numbers from representation theory. So we make a compromise. We say quasi-categorification if the algebra and this is categorified by this monoidal category after you do a base change of this algebra, or in terms of geometry that you do a base change of schemes. So I guarantee that if you do a mild base change, this usually does not change too much about the algebra, and most properties are still preserved. Okay. And now the main result is the following. For almost all the known quantum class algebras which arise from Lie theory, they possess this common triangular basis, or say the analogs of the dual canonical basis. And moreover, when the Gaussian matrix or when the generalized Gaussian matrix is symmetric, these base class algebras, after this base change of schemes, they are categorified by some monoidal category. Okay, so this is our main theorem. And by almost all, I mean, so far, there's a limited number of families of class algebra have been found from Lie theory. And we check most of them except for one family. And in the end of the talk, I will put an appendix where you can see the list of these class algebras. But for technical reasons, let's just skip the very complicated list. And we have a corollary. For some varieties, we have a stronger result. For example, if you take G to be a simply laced semi-simple Lie group, we obtain classifications of its coordinate ring or context coordinate ring. And we also obtain classifications of something called double Bose-Simpson cells coordinate rings, where some new monoidal categories. Yeah. So here, instead of talking about quasi-categorify, we talk about categorify. This means that you do not have to do any base change, and you get exactly the categorification. And now I just want to comment, there's a conjecture for a semi-simple Lie group G. There's a well-known basis of its context coordinate ring called the global crystal basis. It was invented by Kashiwala about 30 years ago using representation theory of this Lie group G. And in some sense, this critical basis, this is a kind of a canonical in the sense of representation theory. And now by extending canonical basis from quantum groups, we get another canonical one, the so-called common triangular basis. So a general philosophy in representation theory is that when we're talking about the canonical structure, there should be only one structure. And then we believe that these two canonical structures should be the same. So this is a conjecture, which I do not know how to do it for the moment. Except in SL2, if G equals SL2, you can compute by hand that this conjecture is true. But in other cases, we don't know. Okay. And there's a comment about the usage of the class algebras. So often there's no well-established quantization of a coordinate ring in literature, because you have to justify why your quantization is good, right? But now if this coordinate ring is actually a class algebra, then there's a very natural quantization in terms of class algebra. And actually, we not only have the quantum class algebra, we also have the integral form. You simply take the base ring to be the Laurent polynomial ring in the quantum numbers. Right? So by taking the integral form, this allows you to specialize v equal to 1, and you get a semi-classical limit. So in this point of view, if you view some coordinate ring from Lie theory as a class algebra, you get quantization and integral form by free. And now finally, before going into mathematical details, I want to talk about the key ideas about how we work out this main theorem. So our main theorem is about many families of coordinate rings share some common structure, right? And usually it's difficult. If you want to do it case by case, it will be a very complicated problem. And here we have the following observation. For many varieties from Lie theory, they can be very different. But if you view them as a class algebra, the class algebra has very closely related combinatorial data. Right? So in terms of class algebra, they are not so different. Sometimes they differ by some base change, sometimes differ by some minor changes. And for this purpose, we introduce something called class operations to relate these class algebras. And these operations, they possess strong properties and have broad applications. And for example, they propagate from one class algebra to another, the structure of class monomials, the basis. They propagate quasi-catalogifications, or if you are lucky, they also propagate catalogifications and more properties. Okay, and now to treat all these varieties, we use the following approach. We do an extension and reduction. So because recall that our varieties come from Lie theory, so there's a Gaussian datum, there's a Gaussian matrix associated with it, right? We first extend the Gaussian matrix to some larger matrix, which must be cosmology type. And we already know the quantum unipotent cell, so this is a special subalgebra of quantum groups for this larger cosmology case very well. And by using the above operations, we propagate the basis and the clarifications for these large quantum groups to the basis and clarifications for the original class algebra that we want to study. Yeah. So this is the basic idea. So why we need to first extend the Gaussian matrix? Because what we know, we already know the quantum groups, as I said in the introduction, we know the quantum groups very well. But if you think about the quantum groups as the coordinate ring over the N or its subvariety NW, so N is like the upper triangular matrix, right? So usually it does not contain enough information to study other Lie theoretic varieties. For example, if you want to study the entire Lie group G, and N is just a subvariety of it, so it is insufficient to go from N to G. But here we first leave the Gaussian datum. We consider the bigger Gaussian datum and with a big size of the upper triangular matrix. But so this until that it contains enough information to study the original Lie group G. So this is the idea. And now, as I said, so all these processes, they happen in the theory of class algebras. So there's a natural question: how can you understand these procedures in Lie theories? Assume that class algebra has never been invented, so you only have a bunch of varieties from Lie theory. And you have N, you have this generally theoretic varieties A, and you have this larger upper triangular matrix until that with a larger size. But in general, for the moment, we don't know if there are any reasonable map like the boson map can connect different Lie structures. But well, it's a natural question. Maybe one day we'll know how to understand this purely in Lie theory. So this ends my introduction. And yeah, is there any question? Okay, so let me proceed to the definition, a brief introduction to class algebra and its common triangular basis. So we start with a toy model. So this is my favorite example. So we consider the Lie group G to be SL3, and we let N to be the upper triangular matrix with diagonal entries 1 here. So this is basically a 3-dimensional manifold. Here we have, for simplicity, we can work over the real numbers, right? So its regular function, its ring of regular function is simply the coordinate rings. Is simply the polynomials in the polynomial ring in the three indeterminates x1, x1 prime, and x2. So this is a very easy polynomial ring. And it has a naive basis, also called a Dup-W basis. So this consists of the monomials in the three variables. And then in the old days, people study the so-called totally non-negative. So a matrix is called totally non-negative if all minors are positive, are non-negative. So here, the interesting minors, they are just the class variables. So they are just the x1, x1 prime, x2, and also there's a 2 by 2 minors here. So these are all the non-trivial minors. All the other minors are either 0 or 1. Okay, so you have 4 minors. You want to check if they are positive or not. And now class algebras can be rewrite as the polynomial ring in terms of these 4 minors, but quotient out the relation among them. So instead you write it as a polynomial ring in 4 variables divided by this relation x1, x1 prime to x3 plus x2. So this relation comes from this determinant relation. And now we see that it has two clusters, x1, x2, x3, and x1 prime, x2, x3. Why is that? So these are two coordinate systems. If you know x1, x2, and x3, and when x1 is non-zero, you can uniquely solve x1 prime. Right? So this gives you a system of local coordinates. And similarly, if you know x1 prime, x2, and x3, and assume that x1 prime is non-zero in your system, you can uniquely solve x1 here. So you have two charts for this n here. And moreover, you can construct a basis in this way. So you take the monomials in x1, x2, x3. So this is, as I said, these are called class monomials in the first cluster. And you take the class monomials in the second cluster. And then they just form a basis of the entire algebra. Because, I mean, you have a naive basis of these 4 variables polynomial ring. But now modular out this relation, x1, x1 prime become redundant. So therefore, you get a basis in this way. And this collection of class monomials, in this example, they are just the dual canonical basis at the classical limit. And I want to say that here, this is a coincidence. In general, the basis is much larger than the set of class monomials. All right. And there's another interesting class algebra here. So you take the subvarieties of this n. So n intersect with this B negative with a lower triangular matrix with possible non-zero with all the possible diagonals. And you take the longest permutation and B inverse. So this can be shown to be the localization of the original class algebra, localized at x2 and x3. So in this way, this is what is it? This is simply the manifold where the x2 and x3 are non-zero. So you can always invert them. And here, x2 and x3, they are called frozen because they are shared by all the clusters. And they generate a split torus, and such that the second class algebra is an algebra over this split torus. Okay, so these are basically our running examples. You see that we have a families of charts, and we have lots of local coordinates, and we have class monomials, and they are related to bases. Okay. And in general definition, assume that you have m vertices, and I denote that from 1 to m to be an interval. And then I call them, and I do a partition. I say that the first n letters are unfrozen for some reason, and they are denoted by red here. And then the remaining letters are called frozen. They are denoted by blue here. This is just like what we have seen before. We have the unfrozen ones. And the chart, or say in class theory, we call a seed. So this consists of a bunch of the class variables. So these are indeterminates, one for each letter. And they are so you should imagine them as the coordinates. Okay? And not only you have these clusters of coordinates, you also have a matrix B tilde. So this is an n by n skew symmetrizable integer matrix. By skew symmetrizable, I mean that if you multiply with some symmetrizers, then you get skew symmetric matrix. And this matrix will be important when you try to do a transition from this chart to adjacent chart. So this gives you the transition rules. We'll see that immediately. And it is often convenient to draw a graph instead of write the matrix. So when assume that the matrix is skew symmetric, namely Bij equal to minus Bji, then we can draw a quiver, so Q tilde, such that Bij is the difference between the number of arrows from I to j with the number of arrows from j to I. So you can use a quiver to represent this matrix. And now, for any of these red letters, the unfrozen ones, there's a process called mutations. This will generate a new seed. So this will be an adjacent chart from the original chart. So it will preserve most coordinates, but only change one coordinate. Xk prime is denoted as Sk inverse, and then the sum of two monomials in the original coordinate. So you put the first monomial when bjk, when you take the power of maximum 0 minus bjk, namely you take the xj with all the bjk negative, and then you take all the xi with the power given by all the bik positive. So this is kind of some definition. For some historical reason, people define it in this way. And there's another way to write this formula. The ratio of these two terms is denoted by yk. I use this red letter to remember that it comes from your red letter k here, unfrozen letter. Then we can rewrite this as sk inverse and take out the first term. So this is the leading term, which is a low-rank monomial in the x1. And then the remaining one is just a polynomial in the y's with constant term 1 here. So actually here is easy, it's just 1 plus yk. As I said, nowadays people have tried to generalize this transition map. So we replace 1 plus yk by more complicated functions in the y's. So, and there's a rule how you replace this original B matrix into a new B matrix, which I omit here. And as you said that, as you have observed that this B matrix, it determines how you define these transition maps. Okay. So in our previous example, we can represent the class algebra in this way. So for our first cluster, x1, x2, x3, we put a seed like this, or we draw a quiver like this. Remember that we can replace this quiver by a matrix. And after mutation, we get another chart, and we have 3 coordinates, and then we can connect them by some matrix, or say connect them by some graph, like this. So so you put a path from 2 to 3 to remember there was a path from 2 to 3, and you invert all the arrows adjacent to 1 here, which you change the coordinates. And you can rewrite x1 prime as x1 inverse, x2 plus x2, and it can be rewritten as x to the power of something, and followed by polynomials in the y's. So these are our running example, and it might seem a bit complicated at first sight, but just remember that for each seed, it consists of a cluster of coordinates together with a matrix, which tell you how you change this coordinate to adjacent chart. And moreover, this mutation, it can be defined or it can be applied to any chart. So you can, again and again, you obtain more chart. So once you are given a chart T here, you can define the Laurent polynomial ring. So there are 2 versions here. You take the localized version. This will be our default choice. So you take the Laurent polynomial ring of all the coordinates, right? So this one. Or there's a partial compactified version. So you compactify the frozen one. So here for the xj here, you do not take the inverse. So this means that you allow them to be 0. So in the first part, xj cannot be 0, right? If you take the spectrum, the first one is a rank M split algebraic torus, and the second one is a partial compactification. So this will be our torus T. And now we also have a frozen torus algebra, as I said before. So this generated by the frozen ones, a split torus. And we can also quantize it, namely in the quantum case where our base ring has a quantum number, we can put the product by we can change the product by insert some V power. So this will be called a V twisted product. It will be non-commutative. So in this way, you obtain some quantization. We omit the details, and because in our talk, we can treat the classical and quantum case similarly. All right. So now we can define the class algebra. We iterate the mutation. We start with any CT. So remember that a CT is essentially a quiver. So this graph is called a quiver, and on each vertex of this quiver, we put some coordinates, right? You start with any CT, and then you can do iterate mutations. You generate more and more chart, or say more and more seed. Right? And now the class varieties, the geometric object, is simply you glue all these chart together, all these torus together, glued by these transition maps between coordinates. And in terms of algebra, the algebra is simply the defined to the ring of regular functions on this variety. So this turns out to be the intersection of all the Laurent polynomial rings. So these are fundamental algebraic set. And in the localized version, where I invert every frozen variables, So this A is this guy A is class variety is a scheme of the spectrum of the Frozen torus. So we'll say A is an R algebra. Okay. So any questions here? Right. So we just emphasize that we start with any chart and we can iterate mutations. We generate something more complicated and we obtain class algebras as a ring of functions on this geometric object. All right, and now let us proceed to basis. Right. So we first recall what is a custom-Lucy type basis. So these are some very special bases. Recall that we have something called Gram-Schmidt algorithm in linear algebra. Say that we have a finite-dimensional real vector space, and we have a basis Z, which is not very nice, and we want to construct an orthonormal basis from the given basis, right? So what can we do? So the elements of Z, assume that we order them from Z1 to Zn, right? So we follow this order, this total order, and we recursively construct UK, this orthonormal basis element, from Zk, but corrected by lower terms from U1 to UK minus 1. Assume that you have already constructed lower ordered elements here, right? So this is basically the idea of Gram-Schmidt algorithm. And now you can view custom-Lucy algorithm as some kind of similar to this process. Assume that you have a vector space not only over the real numbers, but over the polynomial rings R, V plus minus, where you have a quantum number V here, the quantum parameter V here. And this vector space is usually infinite dimensional. And now we let bar to be the R linear involution on this vector space, such that it sends the quantum number V to V inverse. Right? This is the usual operation in quantum groups. And assume that you have a basis which is not very nice. It consists of lots of basis element MW, where for the parameters W in some bigger set, and this set usually it is a lattice or cones, such that this set of parameters, it has a partial order bounded from below, namely it has minimal elements. And we also need some technical conditions about the compatibility between bar involution by this basis element M here, but let us omit the details. And now we use a similar idea. We have a partial order which you can sort you can order the basis element M here. Now you recursively, following this partial order, construct a custom-Lucy type basis or KL basis from this M, such that the basis element become bar invariant. Right? So idea is simple. Assume that MW is not bar invariant, right? You want to correct it by using the lower terms, we'll say low order terms, MW prime or say LW prime. So this is like how we correct ZK to UK here. Here you can also do some kind of corrections. And examples of custom-Lucy bases, these are very famous and important in representation theory. For example, if you start with a standard basis of a Hack algebra, the corresponding KL basis is simply the canonical basis. As far as I know, these are the first canonical basis in representation theory. And assume that you start with the PW basis or the dual PW basis, then apply this algorithm, you get a canonical basis. And finally, assume that you consider something called the grocentric ring of a monoidal category. So this is a category of the finite dimensional modules of UQG hat or quantum algebra. So you get some grocentric ring. And in these categories, you have something called standard modules. And their isoclass form a basis. And now you apply this algorithm, and then you get a new basis. And this new basis corresponding to the simple modules in this monoidal category. Yeah, I think, yeah, this is a very important result. And I think maybe in the type ID, this was first due to Nakajima by using the geometric representation theory. Okay. And now we want to do the same for class algebra, right? So the idea is that you want to start with some reasonable basis, and you apply this algorithm. You want to really get a nice basis. So this is the basic idea. So first you have to choose a chart. It's like when you work with a manifold, you have to choose a chart to do some calculation. You choose any chart, or say you choose any seed here. But the first difficulty is that class algebras usually do not have PW type basis or the standard basis, because it's not a polynomial ring in general. But anyway, for any possible leading grid G, one can construct some distinguished element Mg here. So it has a leading degree x to the power of G, followed by polynomials in the y's, well, with the constant 1. Remember that this y, these are monomials in a yk, where comes from an unfrozen or say red letters. And alpha n, these are just coefficients. And we have to work at the quantum level for this algorithm to work. And now we can sort this collection of elements by their leading degrees using something called dominance order. So we have some partial order that we can do. And now we try to apply the Casan-Lucey algorithm to this starting collection of elements and sorted by some dominance order. But we have some difficulty here. So you do not start with basis, but you only start with a linearly independent set. So this is the first difficulty. And the second one is that your order is not bounded. You have something unbounded, right? So this means that in the end, you will get something unique. You will get unique Laurent series by this algorithm, which are bar invariant and bar involution. But because you do not start with a basis, this is unknown if you get a basis in the end. And because this order is unbounded, so in this algorithm, it might never stop. So you get series instead of polynomials. And to be more precise, these Laurent series are uniquely determined by invariance and such that its transition from L to M is an upper triangular matrix with off-diagonal terms in the negative power of width. For expert, this is a format. If you are not interested in details, so this I just tell you that you have some algorithm generate something good. And now you see that in this definition, your construction depends on some chart, right? And you generate something which you don't know if they are good or not. So assume that you are really lucky. Say that if you have an algebra, if you have a basis L for this algebra, such that it exactly coincides with your output for each chart, with LT for each chart, right? So this means that you construct something. The construction depends on your choice of chart, but you turns out that you produce something which is independent of the chart of the choice of chart, and moreover, you really produce some basis. Then this is called the common triangular basis. Common means that it is for all chart, and triangular means that you have some triangular transition matrix. So this is a very strong definition and a very optimistic one. And in the end, you will always get some Laurent series of this form. So you have a leading term, x to the power of g, followed by polynomials or followed by series in the y's, in theyn's. And I want to say that this looks very much like the characters of highest weight modules, where g give you the highest weight, and Cn, it looks like the dimensions of the weight space. And actually, this is true. So for seeds, or say for chart arising from representation theories of quantum affine algebras, for some good choice of seed, these are exactly the characters of the highest weight simple modules, or was the truncation of the characters, or more precisely. Okay, so they have some representation theory meaning. And as I said, that the common triangle basis in general, this is defined to have strong properties. So we put all the desired properties into its definition. And the price is that we do not know if it exists or not. But fortunately, so far, there's no cases where you can try to define it, but it does not exist. So we don't have contact examples. If we are really lucky, maybe they always exist. But you need some mathematics theory to guarantee the existence, which we don't know for the moment. For the moment, I check the existence case by case in some sense. All right. So any questions so far? All right. So we have talked about class algebra as a ring of functions over some geometric object with lots of chart. And we talk about some way to construct its basis. So this is like the Gram-Schmidt. You start with something which is not good, but then you do the correction. Finally, you get something which you hope to be a basis. And now let us go to the operations which relate different class algebras. Recall that in the class algebras, we have n letters, or say n nodes, where you are allowed to jump to the adjacent chart. But now we choose any subset F here, and suddenly you decide that you are forbidden to jump in that direction. Namely, you freeze F. They become another color. They are no longer allowed to mutation there. Then you obtain a new seed, T prime, by definition, right? Because where you can jump and where you cannot jump has changed. And now assume that for the original seed, you have some functions which looks nice. So you have a leading term x, g, and followed by polynomials in the y's, where the yk comes from the red letters, right? But because you are going to freeze some letters from F here, the yk from these red letters, they are no longer allowed to exist in T prime. So the most naive way is simply you just set yk to be 0. If k is suddenly forbidden, then you just set yk to be 0 in this function. So this is called this is the freezing operator. It frees some Laurent polynomials into something new. And I also say that this map at first sight, so this is just some modification. It is not algebra homomorphism. It is not even a linear map in general. But we have the following result. Assume that the original class algebra possess the common triangle basis. Then after freezing, after you do this change, you get the common triangle basis for this new class algebra. Okay, and moreover, if the original class algebra is categorified by some category, then this new class algebra, which you have less direction you are allowed to mutation, it is often categorified by some subcategory. Right? So this process in terms of category, it corresponds to restrict to subcategories. And here is an example. Here we have a quiver. And so we have 4 red vertices where you can generate a new chart. And we have 2 blue ones. And we have this kind of elements in this Laurent polynomial ring. Well, remember that y is just a Laurent monomials in X here. So in fact, this is the characters of highest weight module. And you suddenly decide to freeze 4 here. Namely, y4 is forbidden. So you simply set all the y4 to be 0. You get something on the right. So here, this one, if you do some modification, this can become the characters of another simple modules for this category. Okay, so this is our first operators. It is elementary. It is not algebraic, not linear, but it works. Okay, and the second is a base change. This is more familiar to us in some sense. Assume that you have 2 seeds and they share the same unfrozen part. Namely, after relabeling the red subquiver, that are isomorphic. So you have some red vertices and the corresponding red quivers are the same. And now we have this result. This was known in a previous work of mine. If the first class algebra has a common triangle basis, then the second one also has a common triangle basis. Yeah. There's a way to write the basis element for the new one. And now actually we can formulate that in this way. So in this paper, in this recent paper, for many class algebra and quantum class algebras, if you consider this class algebra AT as a ring of regular functions, or actually the ring of global sections of the structure sheaf for this scheme A here, and you have AT prime, which is the coding ring of the A prime, right? Then in terms of geometry, A and A prime, they are related by this kind of diagram or a sequence of this kind of diagram of following. So recall that A is a scheme of a Frozen torus scheme. So there's a very small algebra, and A is an A algebra here. So we have a scheme over here. And A prime is also a scheme over this spec R prime. So basically, these 2 algebras, they only differ at the frozen part, namely they only differ at this base scheme. So actually, we can show that they are related by this kind of base change, or say fiber product of scheme. So in this diagram, so A is a fiber product of A prime and spec R over spec R prime. In general, maybe A and A prime is not related by one base change, but they are related by a finite sequence of base change, and the arrows can go both directions. Okay, and now so this is how we understand we change the frozen part. So this is can be understood as a sequence of base change in algebraic geometry. And then there's a natural question: how can we categorize the base change? Which I don't know for the moment. So it will require you to understand 4 categories involved and kind of relate them by functors, which we don't know how to do that. Okay. So let us talk about applications which can be more intuitive at the level of pictures. So here we have 2 seeds. So the first seed, it is described by 6 coordinates, x1 to x8, and with a quiver. This quiver tells you about the transition rules. Right? So actually, this seed, it comes from a class algebra. When one study the subcategories of quantum algebras, UQSL3 hat, it appears in the work of Eknes and Leclerc. Yeah. So the class algebra here is isomorphic to the Grothendieck ring of some category. And well, we already know this class algebra very well in previous work, but assume that we do not know that. Now today we have a different way to consider it using the quantum groups. So we consider this bigger quiver on the right. So basically you add one line here. So this bigger quiver, it is a repetition of the affine Dinkin quiver 1, 2, 3, 3 times, and connected by many small arrows. So this is a bit like the right-hand quiver of affine quiver, but you have to add some arrows about also the right-hand translations. So the class algebras for this, it is isomorphic to a quantum groups. So this is a quantized Coney ring of uniform cells of certain type. It appears in the previous work as well. As I said, we know the quantum class algebra here very well. We know its basis, we know its categorifications. And we want to start from right to left. So these two quivers can be read as the following way. You first freeze 3 and 6, you change the colors. Yeah. So we said that this corresponds to reduce to subcategories. There are some way to do this. And then because 3, 6, and 9, they are blue now, so they belong to this base scheme, belong to this frozen torus algebra. Now you can simply remove all these frozens. So this corresponds to a base change of the algebra. And now in this way, you get all the theory from the right. You can propagate the result of the right to the result to the result for the left-hand side. And for example, on the right-hand side, you have a dual basis element, which you can compute by some computers. And then in T prime, you simply set y3 and y6 to 0, right? And you get something like this. This will be a calculus of modules for this quantum of algebras. All right. And this idea, it works in many situations. For example, we consider this kind of quiver, and the corresponding class algebra is something called double Bose-Simpson cells. And it is associated with, in this example, associated with a fine constant root system and with some braid word. And assume that we do not know this class algebra. And we first consider something we are more familiar with. We enlarge the Gaussian matrix from a rank 2 Gaussian matrix to a rank 3 one. So this is a continuity type. And we insert letters so that you get something you get a reduced word. Now you can write this quiver. It is the class algebra is isomorphic to a quantum group. And now from the known result for the right-hand side, you get the unknown result for the left-hand side. And you can actually prove something more, something stronger. For example, you can even prove that the class algebra for this double Bose-Simpson cell, they actually have the standard basis. This is a PW type basis. And moreover, the triangular basis can be computed from the PW type basis by using the constant routing algorithm, using the lexical graphical order. So this is like the good old days where you work with head algebras. All right. And yes, here is something we studied. Oh, yes. Oh yeah, I forgot to say that for these double Bose-Simpson cells, there's another way to categorize it instead of quasi-categorizations. You first enlarge this quiver, enlarge it to something bigger. And for this bigger quiver, we know it very well. So it is the seed for the class algebra, which is isomorphic to a Gaussian ring for monoid category. So here, it is exactly categorized by a monoid category. Then we can show that in a simply laced finite types, namely in AD type, this class algebra is exactly categorized by some new monoid categories determined by these positive braids, consist of the quantum of algebras module by taking the subcategory. So you can do something stronger. And finally, if you take the Lie group G here, for example, this is SL3, the coordinate rings of G is isomorphic to the class algebra of these four, where you do the partial compactification here. And now as an application, this is a special case of the double Bose-Simpson cells. And as an application, you get that the coordinate ring here is categorized by a new monoid category consisting of quantum affine algebras modules. So somehow we get a quantization, or we get a classifications of the coordinate rings of Lie groups, which I think is unknown before. And finally, I put in an appendix here. So assume that C is a generalized Gaussian matrix and G is semi-simple in the finite type and Cauchy-Peterson in general. Now here, this block contains all the class algebra that is applied by our main theorem. So your C should come from the coordinate rings of some Lie theoretic varieties, where this varieties is Lie group G in the finite type. This is an ongoing work which is not exist in the literature yet. Or it might be a subvarieties of G, like the unipotent cells, unipotent subgroup, or double Bose cells. Or it might be configurations of partial flags, for example, the double Bose-Simpson cells or braid varieties. Or this class algebra might be isomorphic to the Gaussian rings of some categories of quantum algebras. Right? There's one missing case. If you take the simple Lie groups and you take the non-standard Lie boson bracket here, Lie boson structure here, you get some class algebras which is not covered by our main theorem. Okay, so I think my talk ends here, and thank you very much for your attention.
So thank you very much for your very nice talk. Are there any questions or comments? So I have a small question.
Yeah.
In some cases for the quantizing developing algebra of Lie algebra, there is some Ringel-Hall algebra. By using Ringel-Hall algebra, some people studying
Yeah.
this. And also in
Yeah.
some cases, there is some basis for Ringel-Hall algebra. Is there some connection with this kind of basis of cluster algebra and basis in the Ringel-Hall algebra?
Yeah, so maybe you can ask this question in a framework of quantum groups, right? Half quantum groups, right?
Yeah,
So
in quantum group case,
in
yes.
quantum groups, I think yeah, I am not an expert in this Hall algebra approach to quantum groups. So as far as I know, the basis in Ringo Hall algebra, you can construct PW basis in some sense.
Yes, yes.
And right, so here we also have the PW basis. So it is actually our standard basis. So it is our standard basis. And then we or in some sense it is due to our SAM because we are working with dual PW basis. And then I think we also have something called a dual canonical basis. I think that is not very easily visible in Ringo-Hall algebra approach. The canonical basis usually, if you do the geometric approach, namely you take the Lustig's probe sheaves over representation space of quivers, then you get the probe sheaves. And then yeah, that will give you the triangular basis. But I think in Hall algebra it is kind of invisible in some sense. There is a well-known approach that connects the Ringo-Hall algebra to class algebras is that there is some kind analog of the faking map, I think. So you start with a Ringo-Hall algebra of the quiver, of a acyclic quiver, for example, or of a Dinkin quiver. And then there's a map from the Ringo-Hall algebra to the class algebra associated with this Dinkin quiver. There is some kind of map. That is very special. It does not. I mean, it is a very special case. I don't know if it works in other case other than these Dinkin quivers. But yeah, here if you want to work with something beyond the half quantum groups, maybe some work have to be done in this spirit.
Yeah, thank you. Are there any comments or questions? Oh, yes, please.
Okay, thank you for your talk.
Mm.
My question might be really a very general question about the
Yeah.
existence of those bases that you were talking about. Uh, well, do you think that are there any, I mean, are there any set theoretic axioms that could in some way guarantee the existence of those bases? I don't know, large cardinals or something of this sort.
Yeah, thank you for the question. I think, I mean, as I said, so far there's no situation we show the basis that does not exist, right? So if one is very optimistic, so we can hope that it always exists. But then the existence is highly non-trivial, and actually the basis it is defined in an elementary way, but it just like the traditional canonical basis for Haeckel algebras. So to prove that the basis has strong properties, actually there are the hidden structures behind that. So for traditionally, people use geometric representation theory that for these algebras, instead they study the Pearl sheaves over some varieties, and they show that this basis element corresponding to the Pearl sheaves. And here for class algebra, we do not have this general geometric realization yet. But yeah, so the hope is that, I mean, either there is a general framework to show that to realize class algebra in geometric representation theory, and the basis correspond exactly to Pearl sheaves on some varieties. Or there's analogously in terms of algebra, there's a general framework that you can construct many monoidal categories for class algebra, such that class algebra are isomorphic to cosine ring of these monoidal categories, or say as quasi-categorified, namely after base change they are categorified. Then in this way that you take out all the simple modules, simple objects in this monoid category, it will give you the basis. So if you only if you only work with at the level of set or combinatorics, I think it's kind of unlikely that you can get this basis. It's just like you cannot do a set theoretic proof for the traditional canonical basis for Heck algebras. Usually you have to go to something more complicated structures and derive your basis from these more complicated structures.
Well, you know, I thank you for your answer, but you know, I mean, I'm considering this. I mean, with you know, the existence of some large cardinals, they have some strong consequences are on different mathematical structures. So, the, Adel, thank you for your answer. So thank you. Yeah.
Okay, thank you.
So are there any questions or comments? So I think the case, let's thank the speaker again. Thank you very much.
Yeah, thank you.